So in this video, I'd like to talk about the anti-Markovnikov addition of HBr across a double bond. And in the previous video, we talked about the Markovnikov addition where the Br goes to the more substituted position. And I clarified that a better way of thinking about this is that the carbocation or the reactive intermediate sits on the more substituted position. And the reason it's better to think about it this way is because we can use the same logic to explain the regioselectivity in the anti-Markovnikov addition. So let's think about a simple reaction here, again, involving propene. And this time we are adding HBr. But this time we have peroxides. So these are usually represented with this, ROOR. This is a peroxide bond right here. And in this case, what we end up with is we get the Br in the anti-Markovnikov position, and our H ends up here, right? It ends up there. We'll draw the H in red in both cases. Okay, so if you want to memorize this using the terminology that gets taught, which is more substituted and less substituted, that's fine. But I think this chemistry should be understood in terms of the reactive intermediate, because the principle here is just one principle, that a reactive intermediate, a radical or a carbocation, it tends to sit on the more substituted position because it gets stabilized. It's electron deficient in both cases. And that electron deficiency is compensated for by the greater number of alkyl groups at the more substituted position. So that's what we're really observing. So how do we observe this chemistry mechanistically? Well, the first thing that happens is you get homolytic cleavage of the peroxide. And homolytic means, homo means same, of course. So each oxygen atom gets the same number of electrons, we can say. We show homolytic cleavage like this, and basically you can show the formation of a radical, okay? The formation of a radical. What happens next is this. These are fishhook arrows. A half arrow implies a single electron or a radical mechanism. I'll do a video on radical mechanisms in more detail, including initiation, propagation, and termination, and the entire mechanistic cycle. The point being that in this case, we generate this. ROH plus, now we have a Br radical. We have a Br radical. So this is a highly reactive radical intermediate. And now we find that if we react this with our double bonded propene, what happens is one of two possibilities. Basically what happens is this. You can show this if you want to, like this. You get a radical attack on the bromine, and the pi bond homolytically cleaves. And actually, we can show this in 2 steps if it makes it easier. You can show this such that you can basically represent this as a diradical. I don't think it's correct, but just to do the accounting so that it's clear what's happening, this is what we've shown above. Okay. Okay. So we do this radical attack, and you get one of 2 possibilities. The Br can go here, which means that the radical goes here, or the Br can go here, which would mean that the radical would be here. Now, a radical is much like a carbocation. It is an electron deficient carbon atom. It is electron deficient. It is an electron deficient center. This is a secondary radical. This is a primary radical. So here again, we can have another look using an energy diagram, and I think it's always valuable to do this. So we have energy, of course, on our y-axis and the progress of the reaction on the x-axis. We imagine our starting materials, and here we go through a high energy radical intermediate to get to our products. And this is the secondary radical. That's the energy level of a secondary radical. And here is the higher energy required to go through a primary radical. So the energy level to get through the primary radical intermediate is prohibitively high. And so that's the reason that this is the preferred intermediate. It will make this intermediate. Why? Because the electron deficient radical has two alkyl groups stabilizing it via induction. And so what that means is that the product that you get of this reaction, of this chemistry, is the anti-Markovnikov product. In other words, it's the product of this reaction right here, where this radical, what it basically does is it does this single electron fishhook arrow. It abstracts a hydrogen and leaves behind a bromine radical for another cycle of the reaction. So this is the product that you get. Plus, we get another bromine radical. And this bromine radical simply goes back and repeats this chemistry here with another equivalent of our double bond. And this is called a propagation step. And like I said, I'll go over a radical mechanism in greater detail in another video, initiation. This is an initiation step right here, where we generate the radical. But like I said, I'll go over this in greater detail, including initiation, propagation, and termination. And we'll think about how radical mechanisms happen. But the point is, and without getting into too many details on how radical mechanisms work, the point that I'd really like to highlight is that if you learn this chemistry by saying that the anti-Markovnikov product is the less substituted halogen, the halogen goes to the less substituted position, and you learn that the Markovnikov product is where it goes to the more substituted position, that's fine. But the point I would try to highlight here is that in both cases, the reactive intermediate is situated at the more substituted position, because the more substituted position results in the more stabilized reactive intermediate, whether that's a carbocation or a radical. So the principle is the same in either case. And so that's anti-Markovnikov addition of HBr across a double bond with peroxides. And like I said, we'll talk more about the radical mechanism itself in another video.